Now that we've learned about the rules of how to apply significant figures in calculations, let's do a couple of examples. The main thing to keep in mind is that your final answer can only be as certain as the numbers you use to get that answer. And basically, I should pause here and say that the only reason why we even use significant figures at all is because every value that we ever use in a calculation, except for counting numbers and constants, is assumed to be some sort of measured value. So in a way, significant figures, it's a way of actually summing up the amount of uncertainty and error in a measurement, or how precise you know that particular measurement is. So everything was measured by something. Now that's a whole different part of the course when we're going to talk about uncertainty and error, but that's kind of where we're going with all this, and that's why it's really important in science. Okay, so we have a couple of different scenarios. The rules when adding and subtracting values are different than when you're multiplying and dividing and using intrinsic functions such as trig functions and exponentials and things like that. So let's take the simple case first. When we're adding and subtracting, actually the number of significant figures really is not that important. It's more about the number of decimal places, okay? So let me just give you a couple of examples. Part A, we're going to add together these three values of energy. It looks like work or energy, all right? If you want to talk about significant figures, this one, the 5.67 has 3, the 1.1 has 2, and the 0.9378 has 4. However, when we want to determine how many digits or decimal places the answer has, all we do is we look at the number of least decimal places in our values that we're adding. The other way to think about it is that the answer can't have a precision that exceeds the least amount of precision in any one of my values. So clearly in this case, the 1.1 is the least precise because it only has one decimal place. So when you add them all together, you get 7.7078. But that's actually incorrect. You should actually state it as 7.7 joules because there's that one decimal place right there, which matches this value of 1.1 joules. Okay, so go ahead. You can pause the video and try for yourself parts B and C. Okay, so for part B, I got 190. Notice that we're rounding that. We are rounding that down to 190 from 190.8890. All right. And that's because my value for y doesn't even have a decimal place. That's an integer, okay? And for part C, we're limited by one decimal place because both m and n both have one decimal place. And so we end up with 2.1 truncated or rounded from 2.070, okay? Okay, so when multiplying and dividing, it's actually equally as easy, all right, that the number of significant figures in your final answer equals the least number of sig figs in any number in the calculation. All right, so now we're not really considering, we're not interested in decimal places. We're actually interested in the number of significant figures, all right? And I should reiterate, the counting numbers and constants don't affect the number of sig figs. You know, constants like pi, whatever else, you don't factor those in. And I'll give you a couple of examples of those, okay? So the next example, let's do part A together. All right, so this is a problem that's involving a multiplication of two values and then a division of two values, okay? So AB over C, and I give you these values of A. All right, again, notice how we're not really going to care so much about the number of decimal places. We're going to talk about significant figures, okay? So which of these values has the least number of sig figs? Well, clearly it's A. A has 3, and the other two each have 4, okay? So what we want to do is use our calculator and just find out what that answer is. I got 22.70.7473. Don't forget your units, always important. That's a joule squared per second. Okay, so I have to somehow make this value, this long, crazy, somewhat complicated number, I have to round that down to 3 significant figures. And actually, it's pretty easy. I can just throw out the decimal place, and I get 2,270 joules squared per second. Okay, so there's my 1, 2, 3. Remember that this final 0 is not significant because there's no decimal place there. Okay? All right. So pause the video and for yourself try to work out B, C, and D. Okay? For part B, we have an exponential here. Both the values K and T are experimental values. All right. We are limited to 2 sig figs here because 25 years, this value 25 years, is a measured value. Okay. So that ends up being 1.6, and the units, and there are actually no units to this one. Okay. For part C, I got 0.0080. Okay, that has 2 significant figures. They're both right here, the 8 and the 0. These 3 zeros are not significant. Why did I round it to 2? Well, because although my x has 3, my k has 2. Okay, and the last one about the hairdryer, this is an example of a counting number not affecting the significant figures. All right, if one hairdryer uses 1.2 kilowatts, how much power is used by 2? Well, we can still have 2 significant figures in our answer. We're not limited by the counting number 2 hair dryers in this case. Okay, so it's 2.4 kilowatts. All right, and we'll do many more examples in class using significant figures, and you'll be using them constantly in every calculation that you do over the next 2 years in this course. So you'll get used to it, and it'll sort of become second nature to you. Okay, all right. Last year we talked about some units, and we've talked this year so far already about how important units are, that having a universally agreed upon set of units is absolutely critical for doing science and figuring out how the universe works. So it makes sense that we'll spend a little time talking about units in a little more detail. All right, so this idea of a unit, my formal definition is an agreed upon way to take a measurement using particular names and symbols. All right, God, that's boring. Oh, what a boring definition. Okay. So there are 2 different kinds of units. We have what's called a base unit, and that's a unit with no reference to any other units. It's not, you can think of it as not being made up of any other units. I'll give you some examples. As opposed to that, we have the derived unit, and a derived unit is a unit that's made up of base units. Okay. All scientists, we use SI units in science, okay? So we don't use inches and feet and pounds ever, okay? So these are the base SI units, okay? Length, mass, time, electric current, temperature, and the amount of substance. And as I mentioned before in my last lecture, there's actually on some lists you see one more, and that's the intensity of light, which is in well, it's not intensity of light, it's illumination of light, and that's in candelas. But generally we don't really worry about that. These are the more common ones that we use. So there are basically 6 base SI units that we use. Okay, the base unit for each is listed here. Beware, beware, beware that the kilogram is the base unit for mass, not the gram. This is kind of an oddball one. Okay, the symbol, you should be comfortable with at least this symbol, and this symbol. We've been using them. Amperes, we'll study that later. Temperature in Kelvin, we'll study that later. Turns out that degrees Celsius, we also consider that to be an SI unit. So that's equally valid, as it turns out, and we'll talk about that later. The mole you've studied in chemistry, hopefully. We'll talk about that later. Okay, and then this definition over here just tells you how these things are actually defined. All right, we have to have some, exact way of defining what these units are, and this is the way we do it. Okay, all right. So again, any units that are not in the previous table or made up of other units are called derived units if they're made up of other units. You need to be able to recognize base units, derived units, okay, and be able to convert between different units. Here's some examples of some derived units. Let's start with the first one. Okay, forces. We've studied forces, all right? The basic unit of a force is called a Newton. The symbol is big N. Again, whether the letter is upper or lowercase makes a huge difference here. And most symbols for particular quantities are uppercase letters. Okay, all right. Can we express a unit? Can we express a Newton in terms of other SI units? We actually can. There's many ways to do it, but commonly it's not done. check this out. It's expressed in SI base units very easily. So here's my kilogram, my meter, and my per second squared. And really, where does this come from? Well, if you think about F equals MA, okay, this part right here, the kilogram is the M, and the meter per second squared, that's my A. So it would make sense that to express a Newton in terms of SI base units is going to be a kilogram times the meter per second squared. And here are some of the other some other common ones that we use. Here's a joule. Turns out that a joule is a Newton times a meter. You don't need to know these right now, and you'll never have to memorize these. But I'm just showing you how you can express units in many, many, many different ways. Okay? So I think it would be advantageous for you to pause the video and to look at this chart and to work out for yourself. Make sure that all of these expressions in this final column are actually correct. Okay? All right. Okay. Dimensional analysis is our last topic here. And this is super important because we need to, your answers have to always have units. And I guess, I don't know if you've ever wondered, how do you know if you have the right units or not? Or how do you know if an equation is actually correct? The way to check it is by using dimensional analysis, and this is just a way of figuring out the units to check whether a given equation is correct. So the things you have to be able to do, you must be able to determine the units of any quantity. Okay? Don't just assume that an equation is correct, that the units are correct. You need to use square brackets when you do dimensional analysis, and just remember that you can add and subtract only with the same units. For example, you can't add a meter and a second together, right? It doesn't make any sense. However, you can multiply meters and seconds together. That's no problem, all right? When we're performing dimensional analysis, if the units of the left side of an equation match those on the right side, then we say that the equation is dimensionally correct. And let me give you an example here. We'll do it again, examples in class, all right? This equation right here relates the period of a pendulum to its length, okay? T, big T is period, big L is length, okay? Don't worry about where this equation comes from. We will actually derive this equation later when we study simple harmonic motion, okay? But if this equation is indeed correct, it means that this whole bit of stuff on the right-hand side, when everything is said and done, after your calculation, the units had better work out to be seconds for all of this. Well, how do I know that? Well, because over here, the expression is giving you the period of a pendulum, and period is the time it takes for one oscillation or one complete back and forth motion of a pendulum, so it better be seconds, okay? So we're going to verify this, and the way that we do it is this. I'm going to sort of rewrite the equation, but I'm going to rewrite it using only units. And here are my square brackets. Okay, so let me explain what I'm doing here. First of all, the 2 pi, we don't care about that in terms of dimensional analysis because that's a constant. Both of those terms are a constant. So really what we're looking at, what we care about are the units of L, which are meters, and the units of G, which are meters per second squared, because it's even given to you, it's the acceleration due to Earth's gravity. Okay, so I'm rewriting all of this as m over 1, that's my L, okay, which is on top of the fraction, all right? And I'm putting that 1 there for a reason, which I'll show you in just a minute. That's in square brackets, showing that I'm only considering the units. Multiplied by 1 over g, okay? Well, since g is an acceleration, it's in meters per second squared, but since it's 1 over, it's actually the reciprocal, which would be second squared over m, okay? So this is I'm going to put this 1 over g right here. All right, so that's L divided by G. The whole thing we're taking the square root of, so I have it to the 1/2 power. Okay, now if you were to do this simple calculation, it's not even a calculation, it's just variables, right? Multiplying these two things, you'll see that your m's cancel out very clearly because I have an m on the top and an m on the bottom. I end up with, in my next step, I have a second squared over 1 and the square root of all that. Well, the square root of anything squared is itself. Therefore, the entire right-hand side gives you seconds. Okay? So what I've done is I've proven that this particular pendulum equation is dimensionally correct. So if I lost you here, you want to rewind the video, go back and go through my solution again. Again, we'll do lots of lots of problems like this in class. All right, let's do another one. Okay. In this case, in this example, what we're going to do is we're going to figure out what a constant is in a particular equation. That's another very useful thing to use dimensional analysis for. So, in this one, you can pause the video and read the question. You may or may not have seen this equation before. What this equation is this relates, this tells you the force of gravity between two masses, m1 and m2, separated by a distance d, okay? Now, this big G right here is something called the universal gravitational constant, okay? And what we're going to do is we're going to use dimensional analysis to figure out what the units are of that. Now, if you just think about it, just stand back and look at this equation. Don't worry about where it comes from. Don't get freaked out about whether it looks complicated or not. Let's just talk about what these variables are measured in. Okay, force on the left-hand side, that's in newtons, right? Always in newtons, okay? These two masses, each of them are measured in kilograms. I'm talking SI base units. So really, this whole quantity on the top of this fraction, that's a kilogram squared, because it's a kilogram times a kilogram, all right? All of that is divided by a meter squared, because we measure distance in meters, all right? Now, to find the units of G, what we want to do is rearrange the equation and solve for G, and then use dimensional analysis in that way, okay? So, this is something that I expect you to be able to do fairly easily at this point, even without even showing any intermediate steps. You should be able to, or at least develop very quickly, the ability to solve for G by just writing it down and doing it in your head. That's what I expect, okay? So G is d squared times F all over m1 times m2. Then what I'll do is with this, I'm going to use dimensional analysis as follows. My d squared is a meter squared over 1. This is d squared right here, times 1 over m1 times m2. So that's 1 over a kilogram squared times a newton, which we saw in that previous slide is a kilogram meter per second squared. So I'm reducing everything, I'm expressing everything in terms of SI base units only, okay? So when everything is said and done, well, does anything cancel here? Sure. We have this kilogram cancels, one of these kilograms cancels, so that becomes a 1. There are no seconds on top and no meters on the bottom, so we have a meter squared times a meter, which is a meter cubed, and then we have a second squared. So it turns out that G is a cubic meter over a kilogram second squared, and those are the units of this constant, okay? Now, I should point out that you often see this written as a newton times a meter per kilogram quantity squared, all right? Now, what you should do at this point is you should verify that what I have written here is in fact the same as this expression right here. That would be very useful for you, okay?